Hi, the Astro 30 here yet again, and today on Astro's Electronics Lab I'm going to be not looking at anything because I just went into the desk and lost my whiteboard. Greetings, the Astro 30 here. Let's try that again. I don't want to turn this into the Amplifier channel, but here we are. I'm going to do another in the series of will this random crap I found on the internet work? Well, we're about to find out. It looks like a typical, well, in this case class A because of the way it's going to be biased. This is going to be at the half supply voltage point. This runs on 9 volts. BC327 MPN, BC337 PMP, again 800 milliamp each. The astute viewer will notice though something very interesting. We have this 1K5, and I'll post a link in the description where the schematic came from. 1K5 coming off of the output, which I assume is going to be the negative of the speaker here. And the positive of the speaker goes to the VCC line. Now you may be thinking to yourself, well, there's going to be DC current running through this speaker coil plus this 1K5 resistor to apply biasing to this self-biased output stage. And you may be thinking to yourself, odd. So what I want to know is how much DC current is going to be flowing through that voice coil, which will have to be up to testing here. Now this input stage is just a normal BC546 or 547, and it's being first DC biased into class A mode via the output, so it's receiving DC feedback to this transistor and also AC feedback. The AC feedback controls the gain and stability of that transistor so we don't go into distortion. So it's a pretty simple circuit. Shouldn't take that long to breadboard up. So I'm going to breadboard it up, put my 8 ohm dummy load in line with it, first measure to see if the thing even works, and then worry about what's the voltage drop across this resistor. Once we know the voltage drop across that resistor, we can then calculate the current. Then once we know the current, we know how much power is being wasted through the voice coil. Sounds simple? Sounds simple. Alright, and dicking around for about an hour I've got it to work. Now I'm using two 1N4004 diodes there because I don't have two 1N4148s or 918s. So I have to use those two. It should still work, I don't see any reason why not. And I was pre-testing before filming. Make sure you get these two BC327 and 337 round the correct way, or the magic smoke will escape. Pity I didn't catch that on camera. Can anyone see a mistake in my diagram? I'll give you a second. This is an MPN. This is a PMP. This should be a BC337. The MPN is 337, not 327. Even though the original article says the MPN is the BC337. And I still copied it wrong. Okay, well cool. Alright, I got all my test gear set up. Now I'm going to power the thing up. And we do indeed have an output. However, the further you crank it up, the hotter this transistor gets. It's the only one that gets the hottest. This one over here doesn't get as hot. There is that, so in its current configuration, yes, it does work. And I'm just driving it into clipping. Back it off of clipping. I want to say I'm getting close to 2 volt out of that. Oops, that's the wrong way. Turn that down, but the pot I'm using is very finicky. So at 2 volt, roughly peak to peak, that's 1 volt squared by itself is 1 volt divided by 8. That's around about 120 milliwatts. Okay, and to confirm that, we can go 1, don't need to square it, because 1 times 1 obviously is going to be 1, divided by the load, 125 milliwatts. I don't know if it sounds any good yet, but what I want to do is I want to calculate, well, measure more than calculate what the voltage drop across this resistor is. It's actually a 2K2, I didn't have a 1K5. I've got a 1K3 I could probably stick in there. Alright, I got my meter carefully hooked up across that transistor and not shorting anything currently, so I'll just do this as a quick test. 1.2 voltage drop, 1.25. So another voltage drop is 1.25 volt. So using
ohms, it's not just fun, it's the law.
Yep, we can divide that by our resistance to get the current, which is 2200 ohms, equals less than a milliamp. So not too bad. So if you wanted to know what the power dissipation of that is, you take your voltage 1.25 volts and multiply it by the current. That gives us not even a milliwatt. Not too bad. It's really insignificant, but I still really do not like the idea of DC running through the coil. So what I'm going to do is I'm going to move this connection point up to here, the positive rail instead. That was harder than necessary. That's what she said. Okay, let's hook up the supply. Let's hook up the supply. Yes, I'm still getting an output. Albeit it's not the greatest. I'm just wondering if the negative of that speaker can be referenced to ground rather than the positive rail. So I might remove it from said positive rail. And move it over to negative rail. Yeah, it's working across to the negative rail. It's clipping badly. I don't know why it's doing that. Okay, so let me change that 100k out for a 68k because the original was more like 86. So I'll just carefully remove this 100k. And I'll plug in this 68 in its place. That's starting to look a little bit better. Yeah, we're getting now 2.5 volt just before clipping. And the volume control's working a little less finicky now. And these transistors are only getting mildly warm. So in the other configuration it was getting really hot. I'm actually getting more closer to 3 volt peak to peak out. Well, this is turning out to be actually a successful amplifier with some changes. Alright, so I'm going to say it's 2.5 volt peak to peak, divide that by 2, gives us 1.25, multiply that by itself, apparently gives us that, divided by 8, more looking closer to 200 milliwatts. Okay, so next I want to play with the value of the biasing resistor, DC biasing resistor, that 2K2. I've got a variable potentiometer in here set to roughly 2K2, and I've got to turn it clockwise to increase. So I'm going to increase the resistance and see what it does to the output. So crank it up just on, well, okay. The signal's getting weaker when I turn it up. So yeah, it's not making much difference. Oh, that fart stunk. Alright, next I'm going to mess around with the base biasing ground reference resistor on the first transistor here. Got my variable resistor set to around 10k, which is what it was. I'm just going to start increasing the value of that resistance. It is giving a bit more of a cleaner signal. Not sure what value we're at now, but we're now getting a healthy 3.34 volt peak to peak out. Okay, so 3.34 divided by its self, it's 1.67. multiplied by 1.67. Look at that, 2.7 divided by our load. We're closer to 300 milliwatt now. Oh yeah, 348 milliwatt. That's getting a little bit better. And our signal's remaining relatively clean, distortion free. That's for our output stage transistors. That one is getting pretty hot. So we'll just turn that down. You wouldn't be driving it that hard, to be honest. Okay, so our resistance of that pot is now closer to 24k. So we're looking at 22k. I don't actually have any 22Ks. I've got a 33. I don't know if that's going to really affect the results any. So we're going to find out. I'll just insert this where the 10K was. Obviously the variable resistor's been removed. Yeah, that doesn't like that too much when you quickly rotate the control. Alright, let me try the 10K again. Still a bit jumpy. Maybe that's how it was. Right, the resistance of that pot is more closer to 18 kiloohms. So I'm going to call it at 18 kiloohms. Alright, time to stop dicking around, and it's now time for an all-important sound test. I guess you're all waiting for that. This capacitor here at the output is actually a 470 microfarad. I didn't have another 100 microfarad. I might have, I'm not too sure. Anyway, I'm going to hook it up to a speaker now and we'll see what it does. Right, I just realised it didn't actually measure the input sensitivity. My little oscillator was at its minimum, which was 600 millivolts going in. It wasn't even clipping then. I will revisit that before the end of this video. Now, my setup is I've got this crappy G5 amp, just using its speaker powered by the little circuit over here, because it's a nice 3-watt speaker and it's 100 millimeters and has decent bass response, I suppose. And it's hooked up to my computer, so now okay, I'll start a track playing. Okay, I'm going to crank that up more.
Baby, you give me ice and fire.
Okay, right.
You're giving me wind and rain.
So I need to find out where the input sensitivity is.
Baby, you give me midnight.
Doesn't sound too bad.
You whip up my appetite. Don't leave me here.
Certainly speaks loud. That weird thing I was getting on the scope is not happening here. Okay, cool. I think we'll leave it there for that. Okay, this was supposed to be a short video, but it turned into a big, long saga. But got all my test equipment hooked up, oscilloscope up there, oscillator there, so Now I'm going to see what the input sensitivity is. Alright, so you guys can watch the scope. I'm going to wind that up a bit further, almost to the point of full, that'll do. And I'll wind the amplitude on my thing up. Well, we're not that far off it. We're clipping there. Still clipping. Actually, wind that all the way up full. Yeah, I'm not getting much more than that, so now I need to find out what's coming out of that. Close to 600 millivolts by the looks of things. Actually 0.55. So yeah, 550 millivolt or so. And my lowest of my oscillator is about 510, so it's only an extra 40 millivolt. Right, so now I suppose the prudent thing to do would be to measure the frequency response of this little circuit, which is going to be hard with an oscillator like that. Alright, so I don't really need this thing cranked all the way to full volume. Right, so now we're at roughly 0.147 kilohertz, so that's 147 hertz. And I'll just raise this up so we get a good voltage reading. About a volt. Okay. So now I'll just wind this down. Still remaining about a volt. Okay, let me change the frequency from 10 to 100. Well, we've got bugger all output on whatever that is, 10 I think. Start winding up the frequency, and it is cutting it off. It's probably the output capacitor doing that. Starting to slowly come up in voltage. We're now at 0.86, 0.9. Alrighty, so I'm going to say that we're getting a reduction after 170 hertz. 160 to 170 hertz is the lower end. Yeah, I'm going to say 170 hertz. Right, now to do the upper frequency range, we're still at a volt and we're roughly at 3 kilohertz. Start winding that up. Is it me or is it starting to shrink? Let's play with the coarse tuning. 4 kilohertz. We're still at around a volt. Still around about a volt, but it is starting to roll off. So I'm going to say 6.5 kilohertz is where it starts to roll off at the upper end. And so just for completeness, I'll do the middle frequencies between, well, in this case 250 kilohertz and the 3 kilohertz we were measuring from before. It's going down, it's going up. Voltage is remaining relatively the same. We're up to 1 kilohertz now. Voltage is jumping up into a couple of millivolts here and there. But no, it's remaining pretty flat along the 170 hertz to 6.5 kilohertz range, and then it starts rolling off at either end, which is to be expected. If you wanted less bass response out of this, and if you're going to drive a smaller little driver, change that value down to like what it was originally, 100 microfarad. And you should be good. Increasing it, however, will increase the lower end frequency response. So you probably be able to get it down to 20 hertz if it was, say, something like 20 to 100 microfarad. But for what it's going to be used for, it's really unnecessary. It'll work fine in its current configuration. Okay, good to go. And to recap the changes I've made to the original design, this biasing resistor now does not come off of the output point over here, and that's no longer between VCC and the output. It's a fixed 2K2 resistor now going to the positive rail directly, so it's now DC biasing this stage, as it should have been in the first place. Don't know what the guy who drew the circuit years ago was smoking, but speaking of smoking, I've written the correct values of transistors where they should be. Don't do what I did, put them around the wrong way, they will smoke. Something about forward biasing them hard on, that's what she said. Okay, this has remained the same, 10 microfarad 4K7. The base biasing resistor is a 68K, which comes off the output, so it's getting it's DC biasing via the output plus AC biasing to control its gain. You've got an 18K ground reference resistor now here on the first transistor, and that's about the only changes I've made. And of course the output capacitor was increased to 470 microfarad, so I put it as 470 microfarad on the schematic here, so it's clearer as to my tests are valid, so to speak. It produces approximately 300 milliwatts into 8 ohm, and it has a frequency range of 170 Hz to 6.5 kHz, which is not bad. It's alright for amplifying. Maybe a ceramic cartridge out of a turntable or something. Yeah, it works for what it is. Its maximum input sensitivity for full output swing is 550 millivolts thereabouts. And these two diodes are 1N, 4148s respectively. I'm using 4004s. Maybe if you use the signal diodes, it may make a difference to its output. I sincerely doubt it. Anyhow, I'm going to leave that here. And if you enjoyed this video, remember to go down below there and rate, comment and subscribe. And you can always follow me on Facebook, and you can become a Patreon member for as little as $1 a month. I would like some new Patreons, please. Any little bit helps. Anyway, this is the Astro 30 saying see ya. I'll see you in the next video.